Good morning. I must apologize for not being with you in Seoul. This would have been my third trip to Seoul National University, although normally I go to the museum. There's a very wonderful museum here on campus that you should check out, and someone should take my regards to those people. They're really always been great hosts. Well, today we're going to talk about naming and addressing, all the things that you haven't, that they haven't taught you in school. And years ago, when I went to do my first big piece on naming and addressing, actually it was the addendum to the OSI reference model, I remembered reading Dr. Seuss to my kids entirely too many times. You know, did I ever tell you about Mrs. McCabe, who had 23 sons and she named them all Dave? I thought, well, I'll use a couple of lines of that for a quote at the beginning just for fun. But of course, you know, so I went to get them and so I could copy them out just right. And of course, you can't read a Dr. Seuss without reading the whole thing. And when I came to that last line, I was like, oh, wow. It's like Dr. Seuss has been sitting in those meetings with us all these years. So I had to use at least a lot more of it. There's a lot in this talk that they haven't taught you. We're going to have to move pretty fast. Some of it will get kind of subtle, and it's going to be, some of it is it's very straightforward, but it's not quite the way you've been thinking about it. So pay close attention. Some of this will make much more sense after you've seen my lecture on Friday, in which I developed the model in which I've been working with. But be that as it may, let's get into this a little bit. Now, like most problems, Wittgenstein's famous statement 7, that of which we cannot speak, we must pass over in silence, applies here, because we really have to get terms very tightly defined. We need to know exactly what we're talking about. In the end, when we've done the painful work of precisely defining everything, it will be a lot simpler to figure out what all the fuss has been about. At the same time, Wittgenstein's penultimate statement, 6.54, applies as well. That we're going to use some ladders, conceptual ladders, to build things up. And once we've got them, we'll find that we don't really need them anymore. And so let's get started on this. This is probably the most important topic in network architecture. Most things fall from this. If you get this right, things go well. If you get it wrong, things can get ugly, and they are ugly. It's also a very difficult and subtle topic. There are nuances here that are incredibly important. I mean, this is one of these things where things that look very subtle turn out to have immense effects on the outcome. So you have to be very careful. And sometimes it looks like you're talking more and more about philosophy than engineering, which is kind of weird. And actually, you know, there's a fair amount of literature in philosophy on names and naming. The trouble is that very little of it applies to what we've got. I've been through everything from, well, not everything, but I've been through the major works from Frege through Russell and Quine and on up. And while I think that what you learn and how you learn to think in reading that is useful, it doesn't really apply. And when it comes to addressing, there's really nothing about that. I mean, even the geographers haven't really talked about addressing much. But for the internet, our problems are almost all addressing, and they affect us in great and in terrible ways. We've got potential address exhaustion, which looks to be a problem. We've got multi-homing, which is creating lots of grief. Mobility is cumbersome and complex. Router table size is exploding, and many other things sort of come from this root. So let's review, you know, explain what this is all about, and then we'll take a look at how we got here. But let's get back to the fundamentals and get some things nailed down. I know there's a lot of talk around here about, well, we should talk about identifiers, or we should talk about addresses, or we should talk about this. They're all really variations of the same thing. So the first thing we have to get down is naming. And, you know, we'll get some definitions down here. There's nothing really hard about any of this, nothing really unique about this. Just get the definitions down so that we know what we're talking about. Names are taken from a namespace, which is essentially a set of strings. We have a function which defines what can go in the namespace. It defines the scope of the namespace, basically. And we have a function which defines, which does the binding of names to objects. There are some operations we can have on names. We just mentioned one of them. We can assign a name, which means we allocate it from the namespace, but we may not bind it yet. We are essentially reserving it. Then we bind and unbind names. And it's interesting, but Jerry Salzer, in his 1977 paper on naming in computing systems, defines resolve as locating an object in a particular context given its name. So an object cannot be identified without locating it, nor located without identifying it in computing systems. This is just one of the fundamentals. There are various types of names besides just assigning a primitive name to something. We may have synonyms for names, which just means that we're going to have more than one name applied to the same object. Now, we've adopted some nomenclature in some places, which is fairly useful, and that is that objects which can have more than one name, we call those names unambiguous, and objects where we can have only one name and only one name, we say that those names are unique. Similarly, we can have names for sets of names, such that when we go to resolve the name of a set, it has a rule associated with it, and the rule decides how many elements of the set get selected from that. Obviously, a rule that selects all is called multicast. A rule that selects one is called anycast. Rather than debate which is which, I've just started calling all forms of this whatever cast. Synonyms of names or names of sets can be taken from the same or different namespaces. When it comes to resolving names, there are basically 2.5 means to resolve a name: exhaustive search, or we can bury hints in the name that help us where to look for it. The half, of course, is indirection. The name or part of a name points to an object that points to the name. We use this quite often. In fact, indirection is actually important in constructing good systems. Hierarchy, of course, is the most important common form of embedding hints in a name. It tends to impose a topological structure on the namespace, which constrains the names that can be assigned to an object. And then there are search rules which utilize how to use these hints to find what you're looking for. Now, I should say something here about the use of the word topological. When I use the word topological, I mean topology. 99% of the time when the word is used in this field, people do not mean topology. When they say topology, they mean graph. One should learn what the difference is and use the words correctly. Everything up to this point is applicable to all naming, identifiers, addresses, whatever, in computing systems. Now, in operating systems, this has been a subject that was resolved back in the 70s, and actually in the 60s. We had pretty much gotten this figured out, that we realized that we need 3 levels of names. We needed location-independent application names. We needed a logical location-dependent virtual address space, and when we had the physical memory address space. And we realized that all 3 of these were really necessary for a fully functioning system. For communicating processes, the situation's a little different. We had a problem figuring this out. Application processes exist to do work. They do not exist to communicate. It's not the reason we create them. They may do it as part of their work, but they have other things that are more important to them. So how do applications relate to communications? Well, they're going to have to share some state. We know that. They can't be unaware that they're communicating. So what's the nature of the relation between the communication mechanism and the application process? Well, believe it or not, this is actually something that OSI dug into. And they actually found the right answer, although it certainly didn't seem so at first. And like most things in OSI, it came about primarily from a turf battle. OSI was this big honking thing going on in ISO, and there were other people doing stuff in ISO for banking and health and other things. And they were like, well, where do we start and you stop? Or do we all end up part of you guys? Or what's going on here? Now, in the early ARPANET, we didn't really, worry about this. We had used operating systems in our guide, and I always say that one of the reasons the ARPANET was such a great success is because we were all OS guys, not telecom guys. We had the right mindset for this. And we had used OS as our guide for the kinds of applications we first did, FTP, remote login, etc. That was our big game. And it turns out those are a special case. Those are one where you have one per system. The difference here is it's a special case. It doesn't really expose all the important elements, it turns out. So OSI came up with this problem of figuring out, where's the application process? Is it inside OSI or outside of OSI? Or as it was called in OSI, the balls in, balls out problem. Where are the balls? Are they inside or outside OSI? Well, they debated this for about a year, maybe a little more. Got into some really philosophical discussions on the nature of distributed computing and all sorts of esoteric issues. Used to make my head swim. I'd stick my head in once in a while as a rapporteur for the reference model just to see how they were doing, and it was tough. And then they came up with the answer, and when I heard the answer, I thought, oh God, not again. Did you guys wimp out? They said the balls were on the line. Okay? It looks like a standards committee wimp out if I ever saw one. It turns out this is the right answer. In fact, it is incredibly the right answer. It exposes a lot of things. What we had been missing was that there's a part of the application that has to deal with communications. They call it the application entity. There's the rest of the application, which does what the application is supposed to be doing. What makes this so interesting is that OSI figured this out about 1985, and they worked out the theory. But we don't see an example of this until the web comes along. This is basically what we're seeing with the web. In the web, we have an application, which is what is actually more important, rather than the protocol. In all the stuff we've done in the ARPANET or in the internet up to that point, FTP, it was file transfer that was important, not what you were using file transfer for. Generally for user applications, it's not HTTP you want to get to. It's CNN.com. CNN is the application. We don't care about it. That's about the protocol. We care about getting to the application. So this actually helped, this was actually a great insight, and actually it has major implications all the way through once you start to see it. So how does this relate to naming? Well, it actually looks pretty complicated, but it's not really. We can just read them off. We have the application entity, which is part of the application is concerned with communication. The rest of the application process is concerned with the reasoning of the application in the first place. The only problem is the pedants won out in OSI, and they never gave the rest of the application process a name. The pedants always says, well, that's outside of our domain. We shouldn't have to name that. Yeah. Application process may have multiple AEs. They assume from different application protocols. So what does this mean for naming? Well, actually, it's pretty straightforward. We can just read it out. First, we're going to need an application process name. It names the application process. It's globally unambiguous and location independent, but system dependent. They may have synonyms of less scope or the same scope from different or the same namespaces. There can be multiple instances of the process in the same system. You might have multiple copies running the same system. Not a problem. You just have an application instance identifier that's unambiguous within the scope of the application process. The application entities are part of the application process. They're unambiguous within the application process. This is all the minimal scope that you need. You could have multiple kinds of AEs, or you can have multiple instances of them. The example I always give is that we could have a hotel reservation system. The application process is hotel reservation. It might use HTTP to talk to the customer. It might use a remote database protocol to talk to the databases it's updating. 2 AEs, might even have multiple customers it's talking to, have multiple instances of that. Mobile databases, multiple instances of those. Obviously, not every application needs all of those, but the theory needs to have them all. And then, of course, you may want to have sets of these things, sets of applications distributed across different machines. And so we have distributed application name or whatever cast that we already talked about. So how does this apply to IPC? Well, if you come to my lecture on Friday, you'll learn that, in my view, a layer or networking is really nothing more than a distributed application that does IPC, does inter-process communication. So what does this say about our naming, the application? What kind of application is this? Well, it turns out that there are 4 kinds of application entities. There's an allocation AE that manages the creation of flows. There are data transfer AEs to control data transfer. There's a RIB daemon that maintains the shared state among the IPC processes. And, managing IPC with a lower layer. Okay? But what about IPC naming? Well, once again, we can just read it off. It turns out that the application name is essentially equivalent to the address. Or what we really do is we give it a synonym which has limited scope of just within the distributed application, i.e. the layer. There are 3 local identifiers. We've already talked about them. An allocation AE instance identifier, commonly called a port ID. And a data transfer AE instance identifier, commonly called a connection endpoint identifier. Why the connection endpoint identifiers are here and not at the layer boundary is something you'll have to come to the lecture on Friday to understand. But this is where it belongs. The RIB daemon maintains the shared state around IPC processes, and it's justly part of the routing, what we call the routing update. So, so to summarize to some extent, an address is a synonym for an IPC process with scope restricted to the layer and structured to facilitate use within the layer. A port ID is the handle returned to a calling application to refer to the instance of communication unique within its AE. A connection endpoint identifier identifies shared state at one end of a flow or connection. A connection ID identifies flows between the same 2 IPC processes, and it's formed by concatenating connection endpoint identifiers unique within the pair. A distributed application name is the globally unambiguous name for the set of all application processes in a distributed application. So it's essentially the name of the layer. This table just sort of summarizes all that. The thing that's interesting here is how few global names we need. Most everything is local. Outside of the addresses and outside of the limited scope of connection IDs, everything else is local. This is very interesting. Now, the question is, this is the theory. How do we understand how this applies and how we got ourselves into the addressing mess that we're currently in? Well, to understand that, we have to go back all the way to the beginning, all the way to the origins to the ARPANET. Now, remember, the ARPANET was the first large-scale packet switch network built. Nobody had built one of these before. We didn't know what the heck we were doing. So, and we were just going to put up a small network, see how it worked, and probably you have to rebuild it. So for the ARPANET, a host address was your IMP port number. It was the name of the wire coming out of your IMP. So when I tell people that my original network address is 12, I'm saying that we were IMP 12 on the net. We were the 12th IMP deployed in the net. So that's where this all comes from. Okay. Was there a reason? Well, sure, it was easy. We were building an experimental network. Nobody had done this before. We were sort of feeling our way along. Was there a lot of thought given to this problem? Not really. We had a lot more things to worry about. Just trying to figure out how to put software into a computer in those days where, these operating systems were never intended to talk on networks. was a hard problem. How do you make it think it's on a network when it isn't? Or how do you make it think it isn't on, or it is on a network when it doesn't know a thing about networks? The answer is you make it look like a tape drive, but that's okay. And we knew that addressing was a hard problem. We knew from the computing world that dealing with addressing was going to be something different, that required subtlety and careful thought, and we really needed to sort of postpone that. Did it take long to realize we had a problem? Not at all. The first IMP goes in 1969. We came on the net in 1970. 1972, Tinker Air Force Base joins the net. And I remember this distinctly. My boss came in to work one morning. He goes, "Oh, Tinker Air Force Base is joining the net. They want to have redundant connections to the network." And I went, "Oh yeah, good idea." And then I thought, "Oh crud, that's not going to work." Because we named the port. We named the interface. The network wouldn't know that those two wires went to the same place. It wouldn't know to use them as an alternate route. Okay? But I'm an operating system guy. As soon as I said that, I went, "Oh yeah, I know what the answer to this is. We need to have a logical address space over the physical address space." Okay? I mean, this is, we need to name the node, not the interface, as well as the interface, actually. And so, the answer was clear. Now, things sort of percolate for a while. We had a lot of other things we had to worry about in those days, just getting things to work. But the addressing thing was something we kept thinking about. And there was a lot of discussion about it, informally. John Chalk publishes stuff around the late 70s, and he's the first one who sort of says, "Now, guys, look, application name tells you what you want to get to, network address tells you where it is, route tells you how to get there. Three distinct things, and that's where the whole idea that addresses are location dependent but route independent comes from." Later, Jerry Salzer takes this and takes it a step further and does more analysis. When do we need addresses? Well, we need addresses when the wire, i.e. the thing we're using at the layer below, has multiple endpoints. And if you come to my lecture on Friday, you'll see how that arises. Application names map to node addresses map to points of attachment addresses, and routes are sequences of points of attachment. This is how Jerry analyzes it in his 1982 paper, also known as RFC 1498. But networks are more general. We have to generalize Jerry's results to networks because Jerry missed a case that hadn't occurred yet in 1982, and it's understandable he would miss it. So what we see is that directories do the mapping between application names and node addresses, and that was generally the language we used, of all applications reachable without an application relay. Node to point of attachment mappings. Now this is the point that Jerry missed, because multipath routing hadn't happened. We can have multiple wires between the same two next hops. Therefore, you need to know the node to point of attachment mapping of all your nearest neighbors. That implies that routes are sequences of node addresses, not sequences of points of attachment. You have to move up a level. Okay? Now, once you've recognized that, something very interesting comes about. Because now you realize that this last mapping and the directory are the same mapping. They are both mappings between nearest neighbors. We're getting a repeating structure here. Isn't that interesting? So how does this apply? Well, just for academic purposes, let's apply this to OSI. Now, OSI had a big discussion about the nature of the network layer. And after all, this was where the whole connectionless fight came down to run tooth and nail. This is where it had to be solved. And because they were working with everything from X25 and the PTTs to the computer systems and Ethernet and all the things that we wanted to do, they really had to analyze this thing carefully. And they realized that the network layer really subdivided into three sub-layers: subnetwork access, subnetwork dependent convergence, which you used if you had a weak network between two strong networks, and then the subnetwork independent layer. Okay, basically the subnetwork access was the point of attachment of addresses were either data link addresses or subnet addresses like X25 or IP, and then subnetwork independent addresses were at the top of the network layer, like something like CLMP, which is what they proposed. Okay, now that leads us to their architecture, which really was an internet architecture. For better or worse, it's a complete addressing architecture. Of course, with all those 7 layers, you end up with too many addresses, but the good news is that the session and presentation addresses don't really exist. They end up getting nulled out, so we can drop them. And you don't always have subnetwork attachment, okay? Now, how do we apply this to the internet? Well, in the internet, the first thing you notice is all you've got is point of attachments. You're missing half the architecture. I mean, there are no node addresses, no application names, and the point of attachment, not only that, is named twice. An IP address and a MAC address are naming the same thing. So it's a waste of time. The Internet Protocol names a subnetwork point of attachment. This is really weird. And domain names don't really help much. They're just synonyms for IP addresses. Basically, we have no levels of indirection in this architecture at all, where in the OSI model, we had at least 3 levels of indirection. So what should it look like? Well, at this point, it should be pretty obvious. We need to have a provider-independent internet layer over a provider-dependent network layer, or a data link layer, depending on what you want to do. Not just a network layer over a data link layer, as in with the internet. Routing is done with addresses in the layer. Well, duh, where else would it be done? Not with addresses of somebody else's layer, which is what we're doing. So if that's all pretty obvious, why are we in this mess now? Well, it turns out for that, we have to go to the first great internet addressing crisis. In 1992, there's fear that IP addresses are getting scarce, router table size is increasing exponentially. That was really the thing that was scaring us. And we need to do something about this. And, this is a great chance to begin to fix some of these problems that we've known about since 1972. I mean, it has been 20 years. You'd think we'd sort of have this thing under control. So the IB convenes the road process, recommends CLMP as IPv7, basically IP with variable length addresses, and names the node rather than, and hence fixes the multi-homing problem. Well, the IETF goes berserk. At this point, the chair of the IAB, who's a good friend of mine, was receiving 70 nasty emails an hour. People were not nice about this. No OSI, no way, no how. A model, we don't need no stinking model. We've got rough consensus and running code. So what do? Well, we have an IP and G process for which the ground rules were fixed length address, continue to name the interface, at least 20 octets of address space, an open standard. Voila, IPv6 or anything but CLMP. Still no solution to the multi-homing problem. It's been 20 years. Well, all's not well. They make this decision to stick with the interface. And several months later, the light dawns slightly. Name the interface, but root aggregation is a must if we're going to make this thing work, implies provider-based assignment, which means providers must, if you change providers, you're going to have to renumber. What? Kind of shot yourself in the foot on that one, didn't you? Okay, that was an implication of continuing to name the interface. Transition for the new IPv6 is dual stack with a NAT. Once you've got a NAT, you don't need v6. Oops. So how many feet do you guys have? Finally, around 2000, there's been so much talk about this multi-homing thing that people start thinking about finding a way to work around it or to find a solution to it. But given the native reaction to naming the node, we need to find a workaround. okay? The problem is that, what they come up with is that the problem is we've been overloading the semantics of the IP address with location and identifier information. We need to split them. Loc ID split is the answer. We'll have a locator we can route on and a flat endpoint identifier, and that will solve our problem. Guys, remember what Salter said in '77? You can't do one without the other. You get another foot? Okay, V6 is the future. The trouble is, in the late 90s, there's not much interest in V6. Offers no benefit to those who pay for adopting it. They just don't know they want it. For the next decade, there's hype. Better security, better cost, better mobility. In fact, it's all the same as in IPv4. Odell had this great line. It's a dessert topping and a floor wax. IPv6 is all the benefit. Jeff Houston's quote here is just incredible. I mean, it's all the benefit of a minor technology change with all the disruption of a major forklift upgrade. Now, that certainly sounds like a plan for success. By 2000, people are starting to become aware that, or suspect that the architecture is running out of steam. New Arc, Clean Slate, Fine Genie are all hot topics, going forward from this point. There's starting to be a lot of talk about Loc ID split. This is clearly the answer. Houston, we've got a problem. Well, in October 2006, there's a major presentation at the IEPG. Router table size is on the increase due to multi-homing. Moore's Law is not going to bail us out this time. This is a big-time crisis. We're in big trouble. If we don't fix this, we're going to have hell to pay. Interestingly enough, Network World sits on this story for a year and doesn't say a thing, even though they're covering every IETF meeting. Finally, Cisco and others start proposing solutions, mostly requiring patches involving NATs and a bevy of new protocols. This is making everyone nervous, but what else do you do? But we do multi-homing. Well, not really. We kludge it. Because we route on the interface, this forces root aggregation to be provider-based. We saw that. Addresses with common prefix go to the same provider. We can store a single root, okay? To do multi-homing, we must assign provider-independent addresses or assign new AS numbers. Same thing. Can't be aggregated. Root table size increases. Remember what our problem is? Router table size is increasing. With the importance of the NAT, what we have found is every reasonably sized business wants to be multi-home. This is probably on the order of 10 to the 6th, maybe, or greater. No, it's actually 10 to the 7th businesses worldwide. This is way beyond our capability, and now with things like Smart Grid coming on, and they're saying dual home every meter, we got real problems. So why wasn't it fixed? I mean, we've known about this problem for almost 40 years. Isn't it odd that a DoD network touted to survive nuclear attack didn't? Well, lots of reasons were given. One was, well, not that many hosts need to be multi-home. This is back in the early days of it. And I used to argue that, well, no, maybe not, but just all the ones that everyone else wants to get to. So don't you think you want them to be reliable? Not everyone should have to bear the cost for a few. This is my personal favorite. This is classic committee politics. Put a condition on the solution that guarantees that the answer will be so ugly it'll get rejected. Multi-homing will be to different providers. By the time you get there, the TTL will have run out. The packet will be so late, it won't matter, so why bother? Remember, we tried to fix this, and it was rejected. But by this time, Cisco and others have started proposing solutions to multi-homing problem. Mostly require, involving NATs and a bevy of new protocols, in particular Lisp and Loc ID split. This makes everyone nervous. But what else are we supposed to do? This is a crisis. November 2008. Houston, we have a bigger problem. Dave Meyer calls me up and says, I got an architectural issue to discuss. He's come across two problems in implementing Lisp. Both require doing path discovery. Path discovery doesn't scale, well-known result. Lisp won't scale, QED. He suspects that any Loc ID approach will have the same problem. Dave's Why hasn't anybody noticed this? They've been talking about local ID split for 15 years. Why didn't it? Just, hey, don't look at me. I never bothered to figure out why. I got enough trouble figuring, back in the 80s, people used to ask me, Day, you're such a network guru. How come you don't know anything about IBM's SNA? It's got 80% of the market. And I used to, sort of glibly say, well, I have enough trouble remembering all the right ways to build networks without remembering all the wrong ways, too. And I had sort of come to this attitude with respect to the IETF. They were doing so many things wrong, I just didn't have time to keep track of why they were all so wrong. But I said, okay, Dave, I'll look into it and see what I can figure out. Well, it turns out Dave's right. All proposals based on local ID split have the same flaw. Once put in context of the P&A theory, it's obvious. So let's take a careful look at what the locator and the identifier name, right? The locator locates the interface, right? Just like we said, the endpoint identifier locates where we're actually trying to get to. We're routing on the locator, not the endpoint identifier. The locator locates the wrong thing. It is part of the path, not the final destination. Locators are going to be aggregatable like IP addresses. The locators are points of attachment. So, it's no wonder Dave is making running into path discovery issues. It's exactly what he should be running into. Okay? How did they make this mistake? Mainly, I think it's sloppy thinking. There's a sort of myth in the internet that IP addresses name hosts, and we always talk about naming hosts. Of course, they don't. They name interfaces, and that's what you have to really keep in mind for this. There are other people now, of course, who are saying, oh yes, well the end-to-end principle solves everything. It will solve this problem. We can solve this problem in the host. These are poor, misguided souls. Mostly this is an attitude taken on by changing the definition of multi-homing. They think it has to do something with traffic engineering. That's a side effect. It ignores that it might take seconds or minutes, if not minutes, for a host to recognize the problem and do the failover. Remember, the fundamental problem here is that the network doesn't know that two paths go to the same place. This is a problem of delivering, not sending. There is no host-based solution. In fact, if you really come down to it, we don't even solve multi-homing for routers, let alone hosts. So this is why multipath routing was such a problem in the late 80s. There is no solution as long as one routes only on the interface address, which means if local ID split doesn't scale, there's no solution involving routing on the interface that scales, which means that IP is fundamentally flawed. Doesn't matter which version, they're both flawed. But we saw that coming a long time ago. That's nothing new. So what's the IETF Plan B? Plan A. What are all the major research universities and research institutes working on, like you guys? Plan A. What are the vendors working on? Plan A. Still? Talk about scary, guys. This is really getting kind of weird. So what do the vendors say? Well, yeah, okay, there may be some scaling issues with local ID split, but we recommend using it. They are very unlikely to ever be a problem. You mean unlikely as in it's unlikely that a lot of people will default on their home mortgages? I mean, we all know where that went. Don't worry, it won't happen often, only in a crisis. But everything works fine. Well, sure, and as Vince Fuller said in his 2006 presentation, by the time you notice it, it means we're already over the cliff. You want to hear the real pisser? We had the right answer. We've known about this problem since 1972. We've had the answer since 1972. Salzer explained it in 1982. We had the right proposal in 1982 to use a protocol that would actually fix this problem. Why was it rejected? Hubris, NIH, and the failure of university education. If I contend that because none of this stuff like Salzer was taught in any networking class, there were probably less than 2 dozen people in the IETF who understood it. And add insult to injury, The proposal in 92 was already deployed in the routers. The transition was over. We could just worry about moving the hosts, rather than the hundreds of millions of dollars spent on a small incremental step that provides no benefit to your bottom line and is fundamentally flawed. Man, you just can't make stuff like this up. The last 15 years of IPv6 development have been a complete waste of time and money, and now it endangers the future of the internet. The problem was never separating locator from identifier. This is fundamental computer science, CS 101. The problem, at its very least, is separating logical location from physical location. It's impossible to locate something without identifying it. This is a pseudo problem that arises from not having a complete addressing architecture. Okay, and just to really hilarious now, the Keystone Cops, called the RRG, have slowly but surely over the last 4 years are now coming to this idea that, well, maybe that endpoint identifier should be aggregatable. You really think so? Wouldn't that make it into a locator? Gee, I wonder why. There was a joke that circulated in the Eastern Bloc right before the fall of the Soviet Union that said that communism was the longest, most torturous road from capitalism to capitalism. Well, it's turning out that IPv6 is the longest, most torturous road from IPv7 to IPv7. And, we're getting epicycles on epicycles here that would make Clavius proud. And from not being precise in your terms, and it primarily is from not being precise in our terms. As Wittgenstein said, that of which we cannot speak, we must pass over in silence. In other words, if you can't define your terms, shut up, kid. But we're going to give Odell the last word. When all you've got's a hammer, everything looks like your thumb. So let's recap what the principles of addressing are that we've come across in this talk. First of all, scope of layers tends to increase the higher in the architecture. An address is a synonym for an IPC process with less scope and probably structured to be useful within the layer. An address should be unambiguous within the scope of the layer and no more. You start making it longer, you start overloading it with things that's going to start causing you trouble. Roots are sequences of node addresses. The relation of a node and point of attachment is relative and hence irrelevant. This is one of the ladders we can throw away. Once we get this thing straightened out right, a layer routes on its address, just as it should. And all the stuff is pretty straightforward. Since the address is structured to facilitate its use in the layer, it has to be assigned by the layer because the layer is the only one thing that knows where it is with respect to the rest of the stuff in the layer. An address names a locus of processing that removes the header. It does not name the host. Naming the host turns out to be irrelevant. An address should not be constructed by concatenating an identifier in one layer with one from the lower layer. Okay, why? Well, think about it. By doing that, you have made it into a path name through the stack. You have made it root dependent. This is precisely what we were trying to avoid. Addresses in adjacent layers should be completely independent. Ignoring these will lead to complexity and cumbersome solutions, but then you guys already know that, don't you? We can see that from a lot of the papers in this workshop. The implication of these principles. Multi-homing is accommodated by having distinct logical and physical addresses. Nothing new is needed. Mobility is nothing more than dynamic multi-homing with expected failures. You're just doing routing updates a little more frequently. NATs are either everywhere or nowhere. Or to paraphrase Bucky Fuller, NATs only break broken architectures. Changing addresses, this one really caught me by surprise. Changing addresses is simply adding another synonym and letting the old one die out. Ongoing connections are never disturbed. A global address space is unnecessary. Probably never need to have more than 32 bits of address. To understand why this comes about, you're going to have to come to my lecture on Friday. And even stranger, While useful, there is no requirement for a global application namespace. It can be a very useful thing to have, but the architecture doesn't require it. This one has some scary implications. Again, for this you're going to have to come to the lecture on Friday to understand that. The conclusions: most of the problems in the internet today are scaling, multi-homing, mobility, distributed applications, are rooted in not having a complete addressing architecture. If the internet were an operating system, it would have more in common with DOS than Unix. The internet has a quarter of the addressing architecture it needs, maybe even less. There's no indirection in the architecture. Imagine trying to do relocatable code in an operating system without virtual addresses. You know, this is basically what we're trying to do. Loc-ID split was really just post-IPNG trauma. There was such an intense reaction to naming the node, nobody wanted to go there. There had to be a workaround. It turns out there isn't. Now Mrs. McCabe wishes she'd had fixed that problem in the 1970s, but she didn't do it, and now it's too late.